Okay, good morning. This is the 5th class of the fundamentals of the vitreous state. It's a postgraduate level course that we give here at the Federal University of São Carlos. The topic today will be liquid-liquid phase separation, or just liquid phase separation, or glass-in-glass phase separation. There are several terms that are used to describe this phenomenon. This is a very common phenomenon in glass science, which was very popular in the 70s. Many people worked on liquid-liquid phase separation in the 70s in the inorganic glass community. However, for some reason, the inorganic glass community lost interest in this topic. There are not a lot of published articles in this topic currently, but there are many in the metallic glass communities. The metallic glass researchers, they discovered that liquid-liquid phase separation also takes place in glass-forming alloys, and also in chalcogenide glasses. The researchers are finding more and more examples of liquid-liquid phase separation. Anyway, what's liquid-liquid phase separation? Very easy way to see what this phenomenon means is if you try to mix water with olive oil. Try to do it, you immediately see that there will be an emotion. One liquid droplets of oil dispersed into water. This is an emotion. Glass-forming liquids are liquids. So for a number of compositions, you also can find one or more liquid phases dispersed in another liquid phase. And if you don't believe this, by a huge coincidence, I have this expensive perfume here. I'm not disclosing the actual make, but this is a very expensive one that I just stole from my wife's collection of perfumes. She will not attend this class. I think she'll never find this out, but I found that there is one liquid. Let me close this to the camera. One liquid phase dispersed in another liquid phase. So let me pass this to you so you can take a look. These are two immiscible liquids. You don't have to, to try the perfume. It's still good, but for some reason, those guys did not take this phenomenon into account. And so I keep this as a very important sample. In our field, this is a nice glass. This is a glass now below TG with two liquid phases here. You can see that it has a slight bluish kind of color. This bluish kind of color is because it's two glass phases now. They're below TG. They were liquid, now they're below TG. It's one glass inside another glass. And this glass has no transition metals or rare earths. So why is it colored? It's colored because these particles have more or less the size of an adequate size just to scattered light. 400, 500 nanometers, this kind of size range. So it's bluish. There are no crystals inside. If you run an X-ray diffraction experiment with this piece of glass here, you see just an amorphous halo. No crystals inside. It's just particles, glass and glass, phase separation. And people have found this phenomenon many years ago, in the early 50s. But those days, there were no transmission electron microscopes, or even people are not used to do small angle X-ray scattering or any of these sophisticated techniques. So they knew that some of these bluish, yellowish like glasses did not have crystals. So they did not have transition metals inside or rare earths inside. So they wondered for some time why they were colored. So only after electron microscopy techniques became available, they discovered the reason for this color of these glasses. Glass and glass phase separation if you're dealing below TG, or liquid-liquid phase separation if we are dealing with above TG. This is normally a defect. If you want to produce a single-phase glass, colorless single-phase glass, this can be considered a defect. On the other hand, some people have managed to find some applications using this kind of phenomenon. And one type of application is opal glass. See, this is a glass which is opal. It's just translucent, but in this case, the size of the glass particles were larger than the wavelength of visible light, so they scatter a lot light, and the glass becomes opaque. So this is used for decorative purposes or for dinnerware like this one. There are a number of opal glasses in the market. So when you see this product here, this is not a glass ceramic. This is an opal glass produced here in Brazil, this particular one. And there's other types of applications. One which is really interesting, it's called Vicor glass. Have you ever heard of Vicor glass? You know what Vicor glass is? It's a commercial glass with a very high amount of silica. You already know that silica glass, pure silica glass, is very interesting because it has a very high TG, very high chemical durability, high optical transmission, very low thermal expansion coefficient. There are many interesting properties. Pure silica glass is very interesting, but it's very difficult to make because the melting point is very, very high. So one process, and this is the Vicor process that people invented many years ago, is to add B2O3 and sodium oxide to some silica glass, a small amount of B2O3 and sodium oxide, which brings liquid-liquid phase separation. So after some adequate heat treatment, this sodium boron silica glass separates into two phases, and they're interconnected. The microstructure is interconnected. So you then immerse the glass piece into an acid solution, for instance, hydrochloric acid solution, and dissolves the phase which is reaching boric oxide and sodium oxide, leaving a very, very rich pure silica glass matrix. So this is a highly porous glass made of almost pure silica, which results from this process of phase separation followed by leaching, by chemical etching. And then this porous, nanoporous material can be used as molecular sieves, for instance, or as a substrate for catalysis, for catalytic processes, or you can even further heat the glass and sinter, close the pores, and make a glass which is almost pure silica at very low temperatures. Because when we add boric oxide and sodium oxide, the melting temperature drops significantly, many cents of degrees, 500 degrees Celsius or so, and then you can easily make this glass. So this is a clever way to produce either nanoporous silica glass or even dense sintered silica glass at low temperatures, much lower than those used to produce pure silica glasses in the normal process. In summary, there are different uses of this liquid-liquid or glass-in-glass phase separation phenomenon. We are going to take a look today at the kinetics and the thermodynamics and kinetics of this process, and then of its role or influence on crystal nucleation, because the next class will be on crystal nucleation. So I'm going to try to show you that previous liquid-liquid phase separation have an important role in the nucleation growth of crystals. So let's then take a look at the phenomenology of this process, and then a little bit on the thermodynamics and on the kinetics of liquid-liquid phase separation. Do you have any questions so far? Are you all familiar with liquid-liquid phase separation? Have you heard of this phenomenon before? Graziella has, because she took some classes before, but the other guys, you have heard of this phenomenon before? Not many of you, I guess. So let's then take a closer look. I'm going to use the whiteboard before, and then we have some transparencies. But before I use the whiteboard, let me show you a few micrographs. If you use an electron microscope and check some glasses, even if they are colorless, if the size of the liquid droplets are much smaller than the size of visible light, they are colorless. So you may have, some of these glasses may have liquid-liquid phase separation, and you never know until you do some real careful study of transmission or scanning electron microscopy or small angle X-ray scattering. So take a look here. This is a barium silicate glasses show this phenomenon, and you can see the phase separation. In this case, it's a glass treated at certain temperature for some time to develop these droplets. In this case here, the white spherical particles are almost pure silica glass, and the matrix is a barium-rich glass. So some barium silicate glasses, lithium silicate glasses, sodium silicate glasses, calcium silicate, magnesium silicate, some borates, some phosphates. There are many systems which show this phenomenon, and sometimes it's difficult to detect. So the actual glass structure is not homogeneous. The actual glass structure has two or more phases. They're all glassy with their own local order and medium range order and their own chemical compositions embedded in one material. And they have a very significant effect in several properties, including an effect on the crystallization kinetics. So you can see here that one can vary this nanostructure of these materials by changing either the temperature or the time of heat treatment. Sometimes, you see, even a material which has been not treated yet already showed this phenomenon. In the cooling path, when you make the glass, sometimes it's very difficult to avoid the appearance of liquid phase separation because the kinetics is so fast. And you don't know. You think you are dealing with a one-phase glass and you are dealing with a 2 or 3 phase glass. Just to give you a very interesting example, you all heard of the very famous 45S5. This is the famous Bioglass invented by Professor Hench in the 70s. Well, many people have worked with bioglasses, and only recently, maybe 2 years ago, a group at Lehigh University discovered that bioglass undergoes liquid phase separation. Nobody had discovered this for many years, for 30 years or so, 40 years, nobody knew this. So bioglass apparently undergoes liquid phase separation. And many other glasses that are on the market maybe undergo liquid phase separation and people don't know yet. Okay, so this is a type of microstructures. There are many types of microstructures related to liquid phase separation in glasses. Let's take a look now in the phenomenon itself. This is one example. Barium silicate is a very good example because barium is a very heavy atom. So to look for these nanostructures in an electron microscope is very advantageous if one phase has a very much higher electronic density than the other. So to look either with electron microscopy or small angle X-ray scattering, the barium silicates are good model systems to understand the liquid phase separation. So this is the equilibrium phase diagram. Pure silica, 10, 20, 30. This is the stoichiometric composition. Barium disilicate, 33.33% of baria. And it has a liquidus. This is the liquidus temperature. And below the liquidus, several people have worked, including myself, I have worked with this system, has a called Immiscibility Dome or immiscibility region. That means the two liquid phases are not miscible. They are not miscible. So we have an emotion in this area here. So this is temperature, this is composition. And there are two boundaries. The so-called binodal boundary, and inside there is the spinodal boundary. Because there are two mechanisms of phase separation. If you're dealing with glasses in this region here, these droplets are formed by nucleation and growth. Nucleation growth of liquid droplets. If we are dealing with temperatures and compositions here, the phase separation takes place by spinodal decomposition. I'm going to explain this to you in a minute. So what's the idea? This miscibility gap is below liquidus. For other systems, the miscibility gap may be even here, above the liquidus. In other words, when you're trying to melt the glass, to homogenize and melt the glass, the system already phase separates into two phases. So it can be above liquidus or below liquidus. This particular example is a metastable miscibility gap because it's below the liquidus of this system. So we are going to now to do some exercises here in the whiteboard regarding, for instance, we can take a glass such as this composition here, a little bit above TG. There's a TG is somewhere, TG of these compositions here is somewhere at 700 degrees Celsius or so, is the TG of the 33.3% barrier glass. This is the TG12, where the viscosity is 10 to the power 12 Pascal second. So we are working a little bit above TG. Of course, TG increases somewhat with the silica content. Well, we are just at the border, just at or above TG. So let's take one composition, this composition here. We quench a glass, make a homogeneous glass up here, and then quench very fast between two steel plates as to minimize, to avoid or minimize phase separation. And then we heat it up here and see what happens. And then very interesting phenomena happens when we heat this up. Let's divide this into composition, number, this is composition, number of particles per unit volume, and say radius of the particles, and this is time. Time. Temperature T. This composition, for instance, 27% mole of barrier at this temperature. And see what happens. If we could analyze the chemical composition, let's see, this is 25, 50, 75, 100%, say of silica. Percentage of silica versus time. The original composition, as I said before, has, say, 27 mole of barrier. So we come here, start at 27, and heat treat the system. Droplets, if I start with this composition here, droplets of this composition here, say 95% silica, this is pure silica, will nucleate. So we have droplets of silica will nucleate, and then if we increase the time, the matrix will change to this direction here, because if you're taking out silica from the matrix, it becomes poorer and poorer in silica, so the matrix phase change towards the binodal boundary, and more droplets precipitate and grow. So more droplets nucleate in the previous ones, grow, others nucleate, and the previous one grows. So the matrix phase becomes poorer and poorer in silica. So there is an evolution here of silica until this composition here is reached. So the composition of the matrix changes time. Oh, you're right. You're right. The silica decreases. You're right. Let me correct this. Oops. I'm plotting silica, so silica should decrease. Then we can plot the baryon. You're right. Silica we had, let's do better. Percentage of baryon. Percentage of baryon was 27. Started with 27 and then increases to about 30 or so. This is not a good scale. Let me improve the scale here. Let me improve a little bit this scale in this plot. I do a break here, and then we can see that baryon goes from 27 to about 30. Yes, to about 30%. Percentage of baryon in the matrix. This is in the matrix. In the matrix phase. How about the percentage of baryon in the silica particles? In the silica particles, it's here, 5%, it does not change much. So the silica particles will have only 5% of baryon. So this is the particles. Matrix and particles. So the process that happens here up to this point, when the composition of the matrix becomes constant, is nucleation and growth. So nucleation, growth. New particles nucleate, the previous particles grow. New particles nucleate, the previous particles grow until they reach the binodal boundary. But the particles themselves, the composition doesn't change. It's pure, or 5% baryon, 95% silica. Now what happens to the number? Let's take this limiting time here. The number of particles, if we are able to quench the glass and avoid nucleation of these particles, at least in the cooling path, the numbers will increase. Now, the numbers increase, but at some stage, the composition of the matrix phase is constant. So the process has reached this boundary here, It cannot go further. It cannot go further. But I continue to heat treat. I continue to heat treat. So what happens to the number of particles? If I continue to heat treat, I have formed a certain number of particles in the sample. Then I continue to heat treat. What happens to them? The number actually decreases. And this is a process called coarsening. It's a process called coarsening. You know, it starts to decrease. So this is coarsening. Because they continue to grow. The particles continue to grow, to minimize their surface energy. They continue to grow and to grow and to grow, but the volume fraction is constant. The volume fraction, by the way, is given by this segment here, divided by the total segment. So that becomes constant when we reach this position here. But they have to grow. The only way to grow is to steal atoms from the smaller particles. So the smaller particles dissolve back and feed the larger particles. So the number actually starts to decrease. But the radius, the average radius, never decrease. So the average radius grow from here to here, and then slowly, but you know, there is some transition here. So this is, it's known that it grows with the square root of time, and then it continues to grow with the cube root of time in the coarsening stage. Now, if we continue to heat the system, we have a piece of glass, it's in our furnace, we leave it on. During Christmas, New Year's Eve, we leave it on. Several weeks. What will be the final structure or microstructure of this material? It has not crystallized yet. Maybe some systems will crystallize before, but I'm not trying to confuse you. Let's assume that the system has not crystallized yet. It will crystallize later on. What's your prediction for the microstructure of this glass and glass type of microstructure if we continue to heat? 2 layers or just one particle. Here, one particle. This is the final microstructure. That's why I like this perfume. It's one particle to minimize the surface energy. In the end, after a very long time, we should have one particle. And the volume fraction of this is exactly the same as the volume fraction of those many, many particles. If we sum up all the volumes here, it will be equal to this volume here. This is the minimum possible surface area that they could have. And it's here to prove it to you. Now I'm going to do an experiment with this perfume. This was very expensive, but worthwhile. This is the best perfume that I have ever bought in my life, you know. I'm going to do an experiment. I'm going to shake this to break that particle. It's a liquid. This is a, you know, what's the viscosity here, you think? You have attended our viscosity class. What's the viscosity, more or less? What's the viscosity of this thing here? 10 to minus 2 or so Pascal. It's like water, right? You cannot do this in a liquid. You know, the viscosity of this liquid here at about TG will be 10 to the power 12. You can shake it, but nothing happens. But this guy here, I can shake it, you know, and maybe, you know, break that, you know, I have broken that particle in many, many, many tiny particles. And next class, this will take some time. Let's see the microstructure. Now you can see we have an emulsion of many, many, many tiny particles of one liquid dispersed in the other. And let's see the evolution of this microstructure in 1 week to see if it comes back to this. We are now at this stage with this perfume. Let's see if it comes back, or how long it takes to come back to this stage here. And this is because the viscosity is very, very low. If we talk about a viscosity of 10 to the power 12, it may take ages, you know, geological ages or so. It's not in 1 week. But it should come to that position. Is this story clear to you? This is the evolution of phase separation, just the kinetics. Now, what then happens if we move the composition to inside now the spinodal boundary? I have a composition here, say, with 10% of barrier instead of 27. This is a totally different mechanism. This is not by nucleation growth. Spinodal decomposition. It's a continual separation of two phases. For a composition here, we have fluctuations leading to one phase to this side, another phase to this side. Later on, one phase here, the other one here. One here, the other one here. This is a decomposition, it's not nucleation growth. So any tiny fluctuations in chemical composition will separate into two phases. So if we had to do a schematic plot here, for now a glass with, say, 10% of barium oxide inside the spinodal boundary, and this is time axis, then you have fluctuations. Tiny fluctuations, then a larger fluctuation, then an even larger fluctuation. So both phases, one phase will have this composition here, the other one this composition here. They'll both change their compositions. And the size will increase, and will continue. And will continue. An important feature of this is that the process starts by spinodal decomposition, but moves. It doesn't see this boundary and stops here. In the end, it will stop at this binodal boundary. This is an imaginary boundary which just dictates the beginning of the process, not the end. The end of the process is always fixed by the binodal boundary. So even glasses which are inside the spinodal area will separate in a different way, but in the end, in the very end, they will reach a coarsening stage and everything else. The major difference is the beginning. Compositions inside the binodal boundary, they separate by nucleation growth. Inside the spinodal boundary, separate by spinodal decomposition. But in the end, the coarsening process is the same. Even this guy here, in the very end, should finish as this one here. Now you could ask, why? Thermodynamically, why there is this difference? I'm not very good at drawings, but I'll do my best to produce a drawing here in the whiteboard. Let's see if we can do this. If we plot the free energy, thermodynamic free energy versus composition, for instance, the percentage of barrier for this same material, you normally have a plot like this. At one given temperature. We are taking the same temperature. In the free energy of a binary, this is a binary, this is pure silica increasing the percentage of barium oxide. Say if I have a composition right here, that 27% mole of barrier that we are using for that exercise, and small fluctuations, this system is being heated, the chemical composition fluctuates locally. If I have a small fluctuation, so if one phase would be here, this is a fluctuation. Instead of having exactly the same composition here, I'll have a fluctuation. In the thermodynamic classes, you learn that the free energy of a binary system can be calculated by a mixture of both, and we do this way. I'm saying that this is the average composition. I have a fluctuation, so it goes a little bit that way, a little bit this way. The free energy of the system will, in this case, increase. This is an increase of the surface energy, of the free energy. So the fluctuation forms and dissolves back. Forms and dissolves back because it causes an increase of the free energy of the system. But the best way to decrease the surface energy is to form a large fluctuation. That's why I told you that the chemical composition of these fluctuations here are almost pure silica. Then it's a very large fluctuation of this size here. Let's take now a large fluctuation. This one here. See if I can do this. Now, with this very large fluctuation, this is the particles. If you remember, the particles have only 5% of barrier. This is 5% of barrier. Now, checking the same plot, the free energy, it was here, but of this large fluctuation has decreased. It's now here. This is the free energy of this system separated into two phases. One phase one liquid phase with this composition, the other one with this composition. The free energy now has decreased. That's why we need a large fluctuation to decrease the surface energy. That's why the composition of the particles are far away from the composition of the starting glass. The starting glass, remember, was here, in our case, 27% of barrier. But the particles we formed have only 5% of barrier. Smaller fluctuations do not have a future. They dissolve back because they increase the surface energy of the system. The system is always checking itself. It doesn't like to increase its own free energy. It always evolves towards a lower and lower free energy states. Of course, there is an even lower free energy here, which is the free energy of the crystalline state. So the system will continue to evolve after phase separation, liquid phase separation, towards crystallization. It's not yet in the lowest free energy state. Now, why the mechanism of spinodal decomposition is different? As I told you, in spinodal decomposition, we have compositional fluctuations, but they evolve and evolve and evolve continuously. There is not a nucleation of a phase with completely, widely distinct chemical composition. It's just a regular evolution of two phases. And this can also be explained in the same figure. The spinodal decomposition boundaries are determined by the inflection points. See, there is one type of derivative here and one type of derivative here. The inflection points dictate the region of spinodal decomposition. So at this particular temperature, these are the limits or so of spinodal decomposition. These limits here for this temperature would be equivalent to, this point here and this point here. These inflection points determine the spinodal decomposition region. So let's take, if our now original composition is here, inside the spinodal area, and let it fluctuate a little bit. Fluctuations of chemical composition happens all the time. Here, they happen and dissolve back. They take place and dissolve back. But what about here? If I have a fluctuation, a fluctuation here, this is a fluctuation. What happens to the free energy? Decreases. So for this type of fluctuation, there is a spontaneous decrease of the free energy. So there is no thermodynamic barrier. This is the concept of spinodal decomposition. No thermodynamic barrier. Any fluctuation that takes place in the system will propagate. It's spontaneous. You cannot stop it. Spontaneous process. So the system evolves in this way. Two phases, one coming to this side and one to this side, and they only stop when they reach these 2 points here. But if you recall, these 2 points here refer to the binodal boundary. That's why it only stops at the binodal boundary. Okay? This minimum and this minimum refer to the binodal boundaries. And the red points at the inflection points refer to the spinodal boundary. Which, of course, are completely related to the immiscibility gaps. So the regions where the two liquids are immiscible. Spinodal decomposition, no thermodynamic barrier, just a kinetic barrier. Of course, it depends on the viscosity of the system and the diffusion rates. That's why this process is not instantaneous. It takes some time because the system is viscous, but there's no thermodynamics. Yes?
What happens if you have after the binodal boundary, like after...
Here?
Yeah.
No phase separation. There is only phase separation inside the binodal. If you're outside the binodal, like the two guys in the back, they are working with barium disilicate glass. You're very lucky. Okay? Because with barium disilicate, you are working here. No phase separation. Very easy to you. Understand everything what's going on with the glass. Only nucleation growth, a few things, you know, easier to understand, okay? Very easy. But if you want a messy problem to work with, work here. Because you have liquid-liquid phase separation and crystal nucleation always taking place simultaneously. I did not talk about crystal nucleation yet, but things happen at the same time.
But after the binodal boundary, the free energy increases as well.
Well, after the binodal boundary, it's a single phase system. Then it increases. It increases, but it's a single phase system. It's only one glass. Only one glass. Okay, so this is more or less, you know, in half an hour or so, the phenomenology of this problem. Of course, if you have glasses with 5 or 6 components, this is very messy to understand, and more than one phase can precipitate. You can have 3 or 4 liquid phases. It becomes very complicated. But the idea, the kinetic and thermodynamic ideas are summarized in this whiteboard here. Now, since we are going to work with nucleation the next class, next Tuesday we start with nucleation, let me already introduce it to you in a phenomenological way. What's the effect of phase separation on nucleation? And then we'll see in much more detail what nucleation is. But let's take a look now then in the effect of liquid-liquid phase separation on crystal nucleation in glass-forming silicate liquids. As I said, there are many liquids, many types of liquids undergo liquid-liquid phase separation. By the way, polymers also. Several polymers, organic materials and polymers also undergo liquid phase separation, but our focus here is oxide glasses for this class.
Can I ask you a question about what you said before we go on? You're using nucleation as the term for the initial phase separation of the two liquids.
Yes.
So how do you define the critical size of a liquid droplet to say this is phase separated or not?
Yeah, it's the same concept that we use for nucleation of crystals. There is always a minimum critical size, and we are going to see next week, but the critical size is always something like 2 times the surface energy. In this case, will be the surface energy of liquid, of this one liquid inside the other liquid, divided by the delta G. And the delta G is this. The delta G is exactly this, you know, the free energy of the separated system minus the free energy of the single phase system. So we know delta G. If we know delta G, this is delta G. If we know delta G in the surface energy, determines a critical radius. If you calculate, this is something like a few angstroms. It varies with the temperature because both quantities vary with temperature. It normally increases with temperature, but it's the same phenomenon. There is a minimum size, and this is a good question. He is asking, 2 or 3 atoms are enough to distinguish one phase to the other? Not yet. If 2 or 3 atoms are below the critical radius, they will form and dissolve. They will form these fluctuations, they form and dissolve, form and dissolve. Once they reach the critical size, then they are able to grow. And this can be calculated. Actually, this is extremely difficult because this we can calculate well delta G, but the liquid surface energy is a very difficult quantity to get. We can only estimate the liquid surface energy. But with reasonable estimates, you can have an idea, and if you do this, you see there's a few angstroms. For crystal nucleation, I have a much better idea because I have worked so much more. The typical critical size to form a crystal inside the glass matrix is about 10 angstroms or so at TG, 10 angstrom. And 10 angstrom, you can imagine a cube of 10 by 10 by 10 angstrom. That means 100 atoms, 150 atoms or so. I'll give you a surprise next class for you about crystal nucleation. Anyway, so this is like an introduction to nucleation because you have an idea now about liquid phase separation. So let's see how it affects crystal nucleation. This is a work I did many years ago, many years ago. This is Aldo Krajewicz was the supervisor of my master's thesis, you know, last century. I even forgot when I did it. And this is my supervisor of my PhD thesis in England. Unfortunately, Peter James has passed away already, but Aldo is still here with us. Anyway, so this is a tribute to both Aldo and Peter. So let's take a look on this effect. So we are going to, I gave you the introduction about liquid phase separation. So let's see the objective of this class, some experiments and some results. I only took 2 systems because I started to talk about barium silicate and also lithium silicate, and then conclusions. So this I have already told you. Phase separation is a very common phenomenon, very, very common phenomenon. And the question is, what's the effect of liquid phase separation on crystallization, especially in the very early stage of crystallization, that is nucleation? What's the effect? There are papers about this subject I can give you if you are interested later on. So the objective of this part of the class is to shed light on the possible effects of one phenomenon in the other, how we are going to do or accomplish this is to a series of very careful series of experiments using small angle X-ray scattering, transmission electron microscopy, and also optical microscopy. So we had a series of glasses, they are heat treated above TG for some time, and we followed this type of kinetics. We followed this type of kinetics with techniques which allowed us to decouple liquid phase separation from crystal nucleation, because simultaneously with liquid phase separation, crystal nucleation takes place. So we had to use techniques which only look to one and do not look to the other phenomenon. And they're taking place at the same time. So it was a very elegant type of combination of experiments that we devised many years ago. And I think we have some really conclusive results. The experimental parts were, we made several glasses of both systems, just trying to make sure that they were homogeneous, at least above the liquids. They're really well mixed and homogeneous, bubble-free, and so on and so on. And there are techniques to test how homogeneous a glass is. I can tell you later. They were melted, and they are very fast quenched. They're chemically analyzed to make sure that we had the compositions that we wanted, say inside the spinodal, inside the binodal, outside the binodal. And they are heat treated at some temperatures slightly above their TGs. It could heat treat below TG also, but it takes a longer time. So we always choose something, you know, a few degrees above TG, so you can measure this phenomenon in a few hours. And then we use small X-ray scattering, TM, to look for the liquid-liquid phase separation. And then duplicate samples were developed at high temperatures to grow the crystals, if they existed, and were probed with optical microscopy. And that's the key, because optical microscopy, what's the resolution limit of an optical microscope, typically? Maziar, Mina, you are working with optical microscope. What's the resolution limit? How small an object you can see with an optical microscope, more or less?
1 micron.
1 micron. 1 micron. This is the minimum you can see. So 1 micron is much, much larger. If you recall the micrographs that I show you, those phase-separated droplets had 30 nanometers, 20 nanometers. So if you look at an optical microscope, you don't see them. You need small angle X-ray scattering or transmission electron microscopy. So the phase-separated matrix was invisible under an optical microscope, but we could check for the crystals. So the crystals were checked with optical microscopes in the liquid-liquid phase separation with these techniques. Okay. Results. So you have seen this. We have several compositions. I'm not going to show all of you. Only a few. Let's take 1 or 2 compositions here and see what happens when we heat treat these compositions. The microstructures are here. You have already seen these microstructures. There are many microstructures depending on the heat treatment, but look at this size. See, this bar here is 100 nanometers. So the size of each droplet is a few nanometers only. Okay? A few nanometers. even growing at, say, 820 is much above TG. TG of this glass is about 700 Celsius. 820 is well above TG. And look at the size, it's the same bar is valid. It's still a few nanometers. And there are other micrographs. So the numbers, in case you are interested, the nucleation rates were 10 to the power 20. This is a huge, huge nucleation rate. 10 to the power 20 droplets per cubic meter per second. Every second you heat treat this glass, 10 to the power 20 droplets form in a cubic meter. I'm talking about a cubic meter. Many, many droplets form. And the estimated surface energy, this surface energy here, a liquid, this is one liquid forming inside the other liquid, estimated, I can tell you next class how you estimate this, it's about 5 ergs per square centimeters. In the same glasses, you see that the number of crystals will be about 10 to the power 10. So this phase separation forming in crystals at the same time, but the rates are completely different. 10 orders of magnitude difference between the rates with which they are forming. This is some other micrographs just to show you, liquid phase separations here, and this is the arm of one crystal. See, the crystals are much, much, much after we do a development, or a long treatment. This is 30 hours. 30 hours at 743. The crystals have grown a lot, in several microns. This is 1 micron, so this is 30, 40 microns, but the droplets are still nanometer. Anyway, you are not familiar with small angle X-ray scattering, but for the purposes of this class, it's sufficient to know that those guys in the back, they do light scattering. If you do light scattering, you have particles of the order of the visible light. They scatter light. I have shown the blue samples which are floating with you. The blue samples there, that's a color due to scattering of light. Now, X-rays have the wavelengths much smaller, 1, 2 angstrom. So if you have very small particles scatter X-rays. So small angle X-ray scattering is a way to measure the scattering of very small nano-sized particles by X-rays. You don't see the scattering of these particles by light because they're much smaller, by visible light. They're much smaller than the wavelengths of visible light, but they scatter X-rays, and you can see that, this is a particular glass with 27% at 743. 0 hour, almost no scattering, because it was fast quenched, and nothing happens there. And then half an hour, 2.5 hours, 6 hours, 9 hours, 13 hours, 17 hours. See that the intensity of the scattering was increasing because the number and size of these particles were increasing. And then there are laws which allow us from the shape and the areas of these curves to get information, like the size of these particles and several other type of information. So we could follow, this is a way to follow the development of liquid phase separation by heat treating several samples. And this was done in a synchrotron laboratory just to increase the intensity of the scattering, but it can also be done in a normal X-ray diffraction unit with small angle facilities. This is just another glass at the same temperature. So we had several glasses, several temperatures, and following the scattering. Following the scattering, and then I'm going to skip this one. And the one property is that if you integrate the scattering curves from 0 angle to, you know, whatever angle it goes to 0, the integral, this is the integral from 0 to infinity, but it's never infinity. Infinity means up to the point where the scattering goes to 0. This is the intensity, this is scattering angle. If we integrate, can show that it's proportional to the volume fraction, to the number of particles in the volume fraction. Well, what happens when we reach the binodal boundary? The volume fraction becomes constant. The number actually decreases, but it's very slow. This is a very slow process. It's a very slow. So once you reach a constant value, it's because the process has stopped. It never stops, but the matrix phase has reached the binodal boundary. So this is a way to see what time it takes at a given temperature for a given composition for the phase separation process to reach the coarsening stage or to reach the binodal boundary. Here's an example. If we are at this temperature T1 and heat treat this glass, it will go and reach the boundary. So T1, it will go and reach the boundary. Q becomes constant. The same thing for another temperature or another composition. So we are interested in following these kinetics. And you do not have to pay attention to this. This is details on how we extrapolate the experimental curves, how we extrapolate to 0, and then we extrapolate to infinity or to 0 here using 2 laws, but you do not have to know this. Use the Guinea's law and Porro's law to be able to get this whole curve, so then we can integrate them. And here you are, the results. For our 27% barrier glass at 743, the phase separation process was very fast. We could not even check the beginning. I mean, after 2.5 hours or so, that's when we had our first data, it was constant already. Then we moved, that's why we moved to other glasses for which the kinetics is a little bit slower, so we could follow this 28.3% glass, you know, at 743. It took about 6 or 7 hours to be constant. And then after some time, it increased a lot because of crystallization. But at this stage here, phase separation was completed. For the same glass at a higher temperature, it took about only 2.5 hours. As you expect, the higher the temperature, the faster the process. But we are interested in this time to compare with the nucleation, crystal nucleation. This is nucleation of droplets. We want to compare with the nucleation of crystals. So we heat treat the glasses. Of course, there is some heterogeneous nucleation around bubbles or around, this is a platinum particle which came out from the platinum crucible, sometimes you have to discard, but very uncommon. So we discarded heterogeneous nucleation from the sample because we are interested in homogeneous nucleation. And here you are. These are now photographs of 10 microns. So these crystals here have 5, 6, 2, 3, 4 microns, much, much larger than the amorphous droplets. So you could follow by microscopy. And here you are. A glass with 28.3, say one of these glasses here, at 745. It goes, and then reaches a constant steady state nucleation rate. In the glass outside the gap, at the same temperature, had a much higher nucleation rate. This is the stoichiometric glass outside the gap. And this other one is inside the gap. So it was increasing, and then became constant. It took about 7 hours to become constant. It's another glass. And this is the most important result. Remember, here, seven hours or so for this is crystal nucleation rates. About 7 hours. Increasing, 7 hours became constant. This is phase separation. Crystal nucleation, liquid phase separation. 7 hours. So it takes, the two phenomena are completely interrelated. The matrix phase is increasing its content of barrier, and the crystal nucleation rate is also increasing. After 7 hours, for this particular glass, for this particular composition, crystal nucleation rate becomes constant. And this has been repeated to other compositions. See here, this glass was 27%, it's about 2 hours or so became constant. Glass was 27%, 1.5, 2 hours it became constant. The glass with 28%, this time here it takes to become constant. The composition of the matrix phase, if I go back here, the composition of this is the glass with the highest nucleation rate, the stoichiometric glass, which has 33% of barrier. We started with a glass here. He treated the nucleation, the crystal nucleation rate increased, and reached this value here. But this value here, 31% or so of barrier, is smaller than 33.3. So it never reaches the 33.3. But there is a clear correlation with the enrichment of barium. It takes 7 hours to come from here to here. It takes 7 hours for the crystal nucleation rate to achieve its steady state condition. So what's the effect of phase separation? We have done many experiments with many other glasses and many temperatures. It's just a compositional effect. The composition of the matrix is becoming richer and richer and richer in barrier, so the crystal nucleation rates are increasing, increasing, increasing. But they never reach the 33% because the binodal is before 33.3%. This is a purely compositional effect. And I'm saying that because there has been, and there is still, controversy in the literature. Some people propose that the interfaces of the liquid phase separation droplets could act as heterogeneous nucleation sites for crystal nucleation. Some people said, well, you form phase separation, then there's these interfaces, they act as heterogeneous nucleation sites for crystal nucleation. But we are proving here that this is not the case. It's just a compositional effect. Liquid-liquid phase separation causes compositional effects that increase a little bit the nucleation rates, but not so much. It's not like being active catalyzers or active nucleating agents. It's just a compositional effect for crystal nucleation. I have more results, but I think I could stop now, and because this has been a very intense class, and see if you have any questions. Is this clear to you? Yeah? Are you convinced that liquid phase separation causes compositional changes, and that's because the nucleation rates increase?
Eu posso ler em português mesmo?
Pode.
Então, se eu tivesse uma composição fora do domo binodal, eu não teria esse período de indução e nucleação?
Guilherme is asking if you are working here. This is a good question. I was hoping that Maziar would ask that question because he worked on induction times. But anyway, if we are working here, there's no induction periods. The question is, yes, there are induction periods, but our experience demonstrates that these induction times are only measurable close to TG. If you're close to the glass transition, then induction periods are measurable. That's why we have chosen a temperature which is 45 degrees Celsius above TG. So the normal induction times are negligible, as seconds. So these secondary induction times are caused by phase separation. In other words, if you take the glass outside the gap, there's no induction time. See, it starts here at 0. At this temperature, because it's well above TG. This is a good question. Any other questions? Graziella.
In this diagram, you said the maximum crystallization rate is in the stoichiometric decomposition, right?
Yes.
The rate increasing after the stoichiometric composition, it will decrease as well?
Well, after the stoichiometric composition, things become more complicated because you have another phase. You see this 3 to 5 barrier. So if you come here, then you have a nucleation of 2 phases, which may be or may be not higher than the other one. In this region here, that's why you have only this phase, and maybe silica. The other phase will be silica, but silica is so viscous that doesn't appear at this range of low temperatures. So I'm working in a range where there's only barium disilicate is the only phase. But here is unpredictable. It can be higher or lower.
It depends on the interaction of two phases.
Yes, yes. That's a good question also.
How do you that both has the same crystalline phase? Like, did you like the disilicate? You estimate that is like the crystal phase is the stoichiometric one, but when you have the other stoichiometry, is the same crystalline phase that grows?
Yes, yes, because the crystalline phases are dictated by the phase equilibrium diagram. So the phase equilibrium diagram does not see, you know, this binodal and spinodal boundary. They're not seen by the crystals. The crystal phases, the equilibrium phases, only see the equilibrium diagram. So to this side here, the only equilibrium phases are barium disilicate and one of the silica phases, or quartz, or 3D-mite, or cristobalite. Only them. There is no solid solution, nothing in this particular system. Some systems have solid solution formation, but not in this particular system. At this kind of temperatures, the only crystal phase is the barium disilicate. If you go to higher temperatures, you know, there are polymorphic transformations, as you know, of the same stoichiometry again, you know. Okay, so thank you very much. And I have good news to you. There's no homework this week because your glasses, you're lucky because your glasses, the glasses that you have adopted, do not show phase separation. And why they do not show phase separation? Why your glasses do not show phase? How do I know that? They are stoichiometric. Your glasses are the equivalent of barium disilicate. This is your glass. Your stoichiometric glasses do not undergo liquid phase separation, so oof, 1 week, no homework. This is paradise. Thank you very much.